I bet you never thought you'd hear from me again. I'm required to make a video about this assignment. I will also subject you to it. Let's go. Part 1, Zipf's Law. The most statistics-y thing to do to language is to measure the frequencies of words. For this assignment, it was suggested to us that we use the Project Gutenberg edition of the Jungle Book, which I have read, but I don't remember reading, so I don't know if it's good or not. Tell me if it is. Text files are kind of useless for this kind of analysis, because they are strings of characters. We need to convert them to a list of words in a process called tokenization. Actually, tokenization tends to be more complicated than this. If you use the right libraries for this, it can be done in like 10 lines. But you're not here for that, so enjoy the delicious spaghetti code. I'm using regular expressions to strip whitespace and punctuation out of the text. If you are being paid money to do language modeling, never do it like this. Ideally, convert your tokens into numbers, because they're much nicer to work with than strings.
Regular expressions are great, if you don't have a lot.
Now we can start counting words, or more precisely, tokens. Tokens that are equal to each other are said to belong to the same type, so a token is an instance of a type. Counting the occurrences of each type and ranking them all by frequency, we get a very familiar looking plot. Just a few high-ranking types predominate in the text. Zipf's law states that in natural language, the frequency of a word is inversely proportional to its rank according to frequency. In logarithmic coordinates, this translates into a line with slope -1. In our case, we get something very close, but a little bowed out in the middle, which is usual for a corpus of this size. From the data we've collected, we can already build a very simple language model. This kind of model is called a unigram model. A unigram is just a single token in a text. Calling it a unigram implies the existence of bigrams, trigrams, and other n-grams, which we will get to later. But for now, a unigram model estimates the probability of the next token according to the relative frequency of its type. The unigram model calculates the relative frequencies of every type it has encountered in its training data set, and during inference, outputs those relative probabilities. We will test out our model later. Part 2, Mutual Information. Pointwise mutual information is a measure of the association between events. Events that co-occur often get positive values of PMI. Events that co-occur very rarely get negative values. Events that don't influence each other get exactly 0 PMI. We will apply the same formula to pairs of adjacent words in our text. Pairs of adjacent words are called bigrams or 2 grams, though if you call it a 2 gram, I respect you less. This code calculates the PMI for every bigram we've encountered in the text, unless either of its tokens has occurred less than 10 times. These are the bigrams with the most positive PMI. Most of these are collocations. Some of these used to be one hyphenated word. Paragraph F actually comes from the legalese disclaimer at the beginning of the Gutenberg edition of the book. The bigrams with the most negative PMI occurred pretty much exactly once. If they had occurred 0 times, they wouldn't be on the list. Grammatically, they do not belong together, but most of them were separated by punctuation before the tokenization process stripped it out. We see that the probability of the next token is heavily influenced by the preceding context. The next model we build will try to leverage that context. Part 3, Bigram Models. A bigram model estimates the conditional probability of the next token based on the previous one, using a combination of Bayes' theorem and maximum likelihood estimation. If you care to read the code, just pause. Since we've upgraded our models, we'll also upgrade our dataset. We'll use some Wikipedia text because it's longer than a single block. Now that we've got 2 models, we need to compare them against each other. For that we need a metric. Perplexity reflects the average branching factor of our model. It reflects the uncertainty in the model's outputs as the average number of roughly equal options it was choosing between. If there was an outcome the model didn't foresee, perplexity becomes infinite. Instead of calculating it directly as the geometric mean of inverse probabilities, we take the logarithm and exponentiate at the end. I am using a held-out validation dataset to evaluate model performance. Unfortunately, both of our models give us infinite perplexities. This is because they can't foresee n-grams they didn't encounter in training. The first thing I did to remedy this was consolidating rare tokens into a special unknown type, and doing inference using its frequency to anticipate unknown tokens. This has made our unigram model usable and set a benchmark. The bigram model has to beat 1000 perplexity to be better. By setting the threshold for what makes a rare token, I get to decide the model's vocabulary. I settled on a size of 20k for no particular reason. Unfortunately, this doesn't quite work for our bigram model, because unknown bigrams occur even between known tokens. We need to make our model less brittle. Part 4. Back off. The essence of back off is that when the bigram model doesn't know, it should let a unigram model weigh in instead. For unknown bigrams, it outputs a constant multiple of the last token's unigram probability. This strategy is relatively simple, and it's called stupid backoff. It introduces a new parameter, the backoff weight, which decides how strongly unknown bigrams should be weighed relative to known ones. Unfortunately, this score is not a probability, because there is no more guarantee that they sum to 1. To remedy this, I directly normalize them, which takes way too long. We can finally evaluate our model. It's kind of overfitted. The distribution of bigrams seems to shift significantly when the text changes topics. Its sampled sentences are also a lot more coherent than the unigram model's outputs. Now that everything works, let's tune the hyperparameter and wrap this up. I perform a grid search over 5 evenly spaced points in the hyperparameter space. It takes at least 10 minutes. I plot training and validation dataset perplexity relative to the hyperparameter. It looks like our model is having trouble generalizing. In the original paper that pioneers the stupid backoff technique, the authors recommended hyperparameter value of 0.4. We ended up with 1.2, which significantly dilutes the model. Taking a look at some sampled sentences from the model, we can immediately notice that grammatical coherence has really taken a hit. Could I have done better? Probably. There are a lot more sophisticated backoff techniques out there, and I didn't even get into smoothing. Unfortunately, I only had so much time to work on this project. Evaluating the fruit of all my labor on the final held-out chunk of the dataset, we get about 400 perplexity, which is an improvement of 60% or so over my unigram model. Reading these lines into the microphone at 11:35 p.m. on the night of the submission, I feel that it's a real shame that I probably won't come back to this.